It's my pleasure to introduce Mihalis Kolountzakis from the University of Crete, and his talk will be on orthogonal Fourier analysis of domains and tiling.
Thank you. First of all, I would like to thank Professor Rizalski for the invitation and the opportunity to be here. I've not been to Ghent before, and it's a very nice place, very active. Okay. So what I'm going to talk about today
Try now.
Okay. So let me start with the very basic things like all of us know about. Basic Hilbert space theory on L2 of an interval, where we have several, of course, orthonormal systems, but certainly I think one of the most famous is the trigonometric system, the complex exponentials, as we call them. And we all know that they form an orthogonal basis, and since the interval has length 1, it's also an orthonormal basis. So in this Hilbert space, the inner product is just the integration of this product. And with this inner product, we all know these guys are here. If you change the frequencies to be integers and only integers, then these are orthogonal. And we also know that they form a complete system. So every function f in L2 has a unique expansion as a linear combination of the exponentials, and the coefficients of this expansion are the so-called Fourier coefficients of f with respect to the trigonometric systems, which is this. We all know this. We studied this before we enter university. But I would like to show this pairing more schematically like this. We have the space, which is 0, 1, and we also have the frequencies, the integers in our case. The frequencies is what goes up into the exponential. This n here is the frequency. So this set of frequencies, which form an orthonormal basis for L2 of 0, 1, we call it the spectrum of 0. Whenever we have such a set of frequencies, we'll call it the spectrum of the domain. So this is the spectrum of 0, 1. And we also know that we can do the same thing in higher dimensions. So if you have the unit cube, say, in d dimensions, and we allow ourselves these functions, which are tensor products of univariate exponentials, the frequencies now are tuples, d tuples of integers. They still form an orthonormal set, which is complete, an orthonormal basis. And here is the set, here's the domain, and here is the spectrum in dimension 2. So again, we'll call it a spectrum. And the first observation that I would like to make is that in any dimension we're going to be working with, it's a basic fact of life that the density of the set of frequencies is the same as the volume of the domain which we are analyzing. The larger the domain, you need a denser set of frequencies, which is reasonable. You have larger domain, you have more functions to represent, you need more frequencies, a denser set. So by density of the set of frequencies, I mean you take a huge disk or a huge ball of radius r, and you count how many points you have in there, you divide by the volume of the ball, that has a limit, that is the density. Okay? And the basic question we're going to be talking about is, for which domains can we do this? Okay, we can do it for the cubes. Can we do it for other domains? It's almost immediate that you can do it for linear images of domains that you can do it on, but let me show you here some examples. So the top row consists of domains where you can actually do Fourier analysis. You do have a spectrum, you have an orthonormal set of frequencies which are complete. And the bottom row, you cannot. Okay, so on parallelograms, this L shape in 2 dimensions or a hexagon, you can find it. For the disk, for the triangle, for this horseshoe type of domain, and for this domain in 1 dimension, you cannot do it. You will see why. But what I want to show with this slide is that the question of whether you can do it or not is not always. Yeah.
bit more specific, I can always take, say, our eigenfunctions of the Laplacian and can do some sort of Fourier analysis with that?
Now, for me, Fourier analysis is, I say that I can do Fourier analysis on the domain if and only if I can find a set of exponentials which form an orthonormal basis. Okay? I realize that Fourier analysis can take different meanings depending on context, but in this context, I want an orthonormal basis. So here's a more interesting example. Now my domain is in one dimension, and it consists of two half-unit intervals spaced by 1/2. It does have a spectrum, and it consists of these numbers. So it's the even integers union the even integers minus 1/2. That is a spectrum. It can be proved. I'm not going to show you the proof, but just to see what is possible. And I want to make the important distinction that spectrum of a domain is never unique. First of all, whenever you have a spectrum, a set of frequencies, let's say in RD, which can analyze a domain, you can always translate this set by any vector you want, and it remains a spectrum. So, for instance, if you're looking at the classical case, where your domain is 0, 1, okay, you can have your spectrum, which I usually denote by lambda, you can take it to be the integers. But you can also take it to be other sets, like, for instance, this set. Just shift everything by alpha. This is still a spectrum. So it's never unique. And in several cases, it can be, the variation can be a lot more than this. For instance, if you take, let's say in 2 dimensions, although it's true in every dimension, if you take the unit cube, the unit square, one spectrum is the integers, right? The integer points. This is one spectrum, but there are others, not just translations of integers. It is proved that if you can form any tiling of space, and I will explain later in more detail what tiling is, any tiling of space by this domain, like this one, okay? Take any such tiling and pick those points. The lower left corner of every copy. It can be proved that this is a spectrum. And every spectrum is actually of that type. Okay, this is non-trivial, but just as an example. Okay, so let's come to the main conjecture now, which dates back to 1974, which has been driving research in this field for a long time. So the conjecture is this. It was made by FUGLEDE in 1974 and says that omega is spectral, meaning I can find the spectrum for omega, if and only if omega can tile the space by translation. By tiling by translation, I mean that, okay, in more formal language, I take the indicator function of omega, I translate it at the locations described by the set capital T, I add them up, and I get a constant. Okay? We usually describe tiling in a more geometric language, like we take the copies, take our set, and we copy to the locations of T, and these must be disjoint and cover everything exactly once. That's how we usually describe it. I prefer this form, which is valid for almost every x, because if you describe it geometrically, you must always clarify what happens at the boundary and where you allow double coverings and where you don't, so I don't want to deal with this. So I just demand this equation almost everywhere in x. So this is tiling. And FUGLEDE says that then and only then it is possible to have a spectrum. So for the hexagon, which you can clearly tile, the FUGLEDE conjecture says, yes, it has a basis. We can actually write it down. So this is the conjecture, and why? Well, I mean, FUGLEDE was not doing this kind of geometry, but he was doing PDE, right? And he had reduced this question, which you see here, to the previous one. So he wanted to do the following. He starts with a domain omega, and he looks at the partial differentiation operators, which commute if you apply them on smooth functions. But if you want to extend them to L2, where you can actually not differentiate things, when can you extend the partial differential operators to a commuting set of self-adjoint? This was the question that he was interested in. and he reduced it to the previous one. You can do it if and only if your domain is spectral. Well, he only proved one direction. The other one is true under some conditions, but I don't want to get into this. So this is where it came from. But we will not be seeing this question for now. Okay? All right. So what we are going to need, though, is an extension of the tiling situation, not from sets to functions. So previously, we were translating a set, and we expected it to cover everything exactly once. But we can generalize it. It doesn't have to be a set. So previously, we had an indicator function here in place of f. Just put anything. Take any function f and translate it around where the locations of capital T. Add them up. If you get a constant almost everywhere, we call this a tiling. And we'll see that f tiles with T at level L. And we demand some absolute convergence. Usually this function f will be non-negative, so there's no question about the convergence. Okay. So what is the Fourier transform we will be using from now on? It's this one. This is my favorite form of the Fourier transform because it has the property that it takes the integers to the integers in some sense. So the first thing we're going to do when we're studying orthogonality of exponentials in omega is to express this orthogonality using the Fourier transform of the indicator function of omega. Now how do we do this? So the inner product in our space in L2 of omega is this. Now if you multiply this with the conjugate of that, you will get exponent lambda minus mu up here. You get exactly this with xi being lambda minus mu. So what you actually get is that the inner product of E lambda and E mu is the Fourier transform of the domain at lambda minus mu. So orthogonality for two frequencies, so by saying that two frequencies are orthogonal, I mean the corresponding exponentials are orthogonal. Two frequencies are orthogonal if and only if their difference lies in this zero set. This is the most basic geometric object in this field, the zero set of the Fourier transform of the indicator function. If you can understand this set, you can solve problems. If not, then probably you cannot. So this set here will be very, very important. So for two frequencies to be orthogonal, the difference must be in the right set. Okay. Now let's take some set of frequencies for a given omega. If they are orthogonal in omega, then for any orthogonal set of functions, you can write down Bessel's inequality, which is what? In our case, so this is to normalize the function to be of norm 1. So the sum of the Fourier coefficients of f squared is less than the normal f squared. This is Bessel's inequality. Always true for any orthogonal set. Now apply this for the specific f being another exponential frequency t, any t. Do the algebra and you get this. So this is the indicator function of omega Fourier transform squared. This is because of this square. And you sum it up over all the lambda and you get at most omega squared. So orthogonality implies this condition, which I have called a packing condition. Why did I do this? Why did I call this a packing condition? In discrete geometry, tiling is the intersection of two situations. Packing, which means you have your objects being disjoint, and covering, which means your objects cover everything. If you can do both with a certain capital T, you have both a packing and a covering, which is a tiling. Packing means everything is covered at most once. Covering means everything is covered at least once. If both happen, then everything is covered once. So this condition, if you have a function f and you translate at the locations T, this is tiling, this is packing, and this is covering. Okay? This is packing. And this is exactly what I have over there, where f is this function, this non-negative function, otherwise called the power spectrum of omega. So this is covering. Okay? So the orthogonality translates into a packing situation. I take my function the power spectrum of omega. I translate it around, and I never exceed level 1. That's orthogonality. And what is completeness? So to have a basis, you need orthogonality, you also need completeness. What's completeness? Well, for completeness, Bessel's inequality must become an identity, an equality. That's when you have completeness. So this becomes an equality, and this is your condition. And this is now a tiling condition, exactly this, only with a different constant. You have to take this constant and divide if you want to have 1 here. So orthogonality is equivalent to packing. Orthogonality plus completeness is equivalent to tiling. Tiling at this level, omega squared, times with this function. And from this form, it now becomes relatively intuitive why the set lambda must have density equal to omega. Because look at this. You have an object, this object, which you're copying around at the location lambda. How much mass are you putting around? Okay, this has mass. What is the mass of this guy? The integral of this, by parsecle, will be the integral of this, which is omega. So you have an object of mass, total mass omega, and you're moving it around. Let me denote it like plus lambda. You're moving it around where lambda says, and you create level omega squared. So you have an object of mass omega, you're moving it around, and you reach omega squared. Well, this density of this, then, the density of lambda must be omega. Because you're repeating this often, this mass, and you get omega squared. That's more or less the proof. Of course, to write down the proof, you need to cut and take limits and stuff like that. Okay, so we have managed to write FUGLEDE conjecture in a completely tiling form. So what does FUGLEDE's conjecture says in this language? It says the following: omega tiles, always by translation, tiles at level 1 if and only if its power spectrum tiles at level omega squared. And now all of a sudden, FUGLEDE's conjecture acquires a sense of at least being a reasonable thing to say, because in the previous statement you had omega tiles at level 1 if and only if omega has an orthonormal basis of exponentials. Why would that be? Well, because now we have seen this is equivalent to another tile. Schematically, here is omega, and here is its power spectrum. This guy tiles if and only if this one tiles. This is what FUGLEDE's conjecture says. The intermediate guy is the Fourier transform of this, which is the convolution of omega with omega through parallel. So this is the FUGLEDE conjecture. We have tiling on both sides. So to understand FUGLEDE's conjecture, we need to understand tiling. So let us now put aside FUGLEDE conjecture for a while and just try to understand what tiling is, tiling by translation, studied on the Fourier side. Why do we want to do this? Because the Fourier transform arises here. It's very natural. So how do we do this? First of all, we encode the set of translations, this capital T, we encode it with a measure. We put a Dirac mass at every point T. And why do we do this? Because we can then write this condition, the tiling condition, which means that this sum is a constant. We can just write it as a convolution. This convolution here will make, so if nu is this measure, if we take nu to be this measure, then f star nu is exactly the left-hand side of this one. Okay? And when you write it this way, so for us now tiling has become this. F tiling with T means this convolution, 1 or whatever constant you want here. And then, of course, when you see a convolution and you are appropriately trained as a student or whatever, you immediately want to take a Fourier transform. They play very well together. So in the Fourier side, f star mu becomes f hat times mu hat. Much easier to understand. Okay, so having this being a constant, which means f tiles with t, is equivalent to this product. F hat times delta hat is a constant times a Dirac mass at the origin. This is the Fourier transform of the constant. Now, some care is needed because, usually f hat is just a continuous function because f will be in L1, but delta hat is not necessarily a function or even a measure. It's in general a temporal distribution. So one needs to be a little careful. But let's pretend we don't see this. We just act formally for the time being. So this product on the left-hand side must live where the right-hand side lives. The right-hand side only lives at the origin. So everywhere else, these two guys must kill each other. Meaning that delta t hat can only survive where f hat is 0. Right? When you have the product being equal to 0, one or the other must be 0. So the only way for delta hat to be non-zero is for f hat to be 0. In other words, the support of this object is contained in the zeros of f hat plus this point. That's always in. Because delta not, because it's at the origin. That's a necessary condition. It requires some formalities to prove it, but I think it is intuitively clear why it should be true. And it's almost equivalent. You can also go backwards. In many cases, but not in all cases. You see, if you have this, then don't you say immediately that these two kill each other? Well, not quite. If you have a continuous function, f hat, multiplied by a measure, such that the measure lives on the zeros, then yes, it kills it. But if you multiply this continuous function by a temporal distribution which lives on the zeros, for instance, a derivative, then it doesn't kill it. For instance, if you take this function, x, and you multiply by the derivative of delta naught, don't get 0. Although the support of this guy is exactly at 0. The result is not 0. So to go backwards from here, to go from here to there, you need to know something about the order of this temporal distribution. It's not immediate. Now this usually rarely causes problems in actual practice, but I want you to keep this in mind. So here we have the 0 set of f hat of the tile, and our temporal distribution lives on this thin set. If we're lucky, this thin set will be just points. In higher dimension will be curves and so on. But this is what I will be calling from now on the spectral condition for tiling. So tiling can be expressed on the Fourier side. And on the Fourier side, it means exactly this. That the Fourier transform of the translates lives on the zeros of the object. So again, you have to understand this set of zeros very well. Now let's take a break here with some history. So I imagine most of you who are of some age have heard of the Scottish Cafe. The Scottish Cafe was a cafe in Lvov, today's Ukraine, then Poland, where about 100 years ago, some very good mathematicians who later became very famous would go there every day after work and exchange problems, drinks, make bets, and they had a big notebook that the waiter kept behind the counter and gave it to them. When they asked for it, they recorded problems, they recorded solutions. Now these people like Banach, Steinhaus, and Ulam showed me. I mean, they created modern analysis in the early 20th century. So some people have collected these problems, and we have access to some of them. One of them is this. And I really want to show how things which back then, for those guys, seemed hard and perhaps interesting, nowadays are completely trivial. So what was the question? Number 181 by Steinhaus. asking essentially this. Can we find it in one dimension? Can we find an analytic f which is strictly positive everywhere, such that, as I denoted here, it tiles if translated as z. It's written explicitly here. We want this to be true everywhere. Not only did they ask if there exists such a function, but they proposed a candidate. And this is the interesting thing. The candidate they proposed, I guess Steinhaus himself, was the Gaussian function, e to the minus x squared. And if there is anything we learn when we learn Fourier transforms nowadays, is that e to the minus x squared is the Fourier transform of itself. So no zeros. If you take this function f and try to tile with it, f hat will have no zeros. You cannot even start the game. There are no zeros. You can never find such a set on which to support your distribution. So if there's any function which never tiles, is this one, and this was the one proposed by Steinhaus to fulfill this problem. Of course it doesn't. Right? So, but it's actually, having seen what we've seen so far, we can actually solve the problem. And here's the solution. So, for f to tile with z, according to the condition we described before, what must happen? F hat, the Fourier transform, must vanish at all the integers except at 0, and must have integral 1 because you want the level of tiling to be 1. This is completely unimportant. But as we said, e to the minus x squared has no zeros, so you cannot do this. But how can we do it? Here's how you do it. You design f hat, not f. And the first thing you do is you take care that your f hat has compact support. So f is analytic. That's immediate. Compact support implies the Fourier transform is analytic. And then, since you want non-negativity, you remember that if I take this function, let's say 0, a minus a, take this to be 1. If you take the Fourier transform of this function, you get something non-negative, the Fourier kernel, that's how we call it. The Fourier kernel is the Fourier transform of this. But this guy has zeros. It has zeros, and the zeros actually come periodically at multiples of a given number. But in the question that Steinhaus posed, we wanted strict inequality everywhere. So what do? Well, we take two of those guys, and we add them up. But we take care that those numbers b and a are incommensurable, say 1 and root 2. And this means that when you add the Fourier transforms over here, the zeros will never coincide. So you will never pick up a 0. One of the other is going to be positive. So if you add them up, this is what f hat will look like. And the Fourier transform is analytic because f hat is a valid support. And has no zeros. And it certainly vanishes, if you take a and b to be large enough, certainly vanishes, let's say, outside minus a half, so it vanishes on all the integers. So it tiles. It's really extremely simple if you just look at it by today's language and today's knowledge. It's sometimes both helpful to see how much smarter we are than those guys, but then if you dig deeper, you realize it doesn't happen. So don't dig too deep always. Alright, so the same stuff that we talked about translating by the integers are actually nothing new. I mean, you've seen this in other language before. It's a so-called periodization of the function. If you start by an arbitrary function on the real line, like this one, and you repeat it at all the integers, do this, and you add them up, so you get this red function. In this example, this is the so-called integer periodization of little f. So capital F is the periodization of little f. And why is this important? Okay, first of all, it's periodic. So when you study Fourier, on the Fourier side, you only look at coefficients, not Fourier transform. But the Fourier coefficients of the periodization are exactly the same as the Fourier transform of the original function at the integers. So in our tiling problem, you want this to be a tiling, which means exactly that capital F is a constant. The periodization is a constant. But for a periodic function to be a constant, the Fourier coefficients, except for the 0th one, must be 0. And what does it mean? Since the Fourier coefficients of f hat are the Fourier transform of little f, our previous condition, this is just to show you that I didn't really say anything new, at least when the integers are concerned as translates. You already knew this. Of course, the theory which I presented you does not restrict itself to integer translates, and if you don't have integer translates, then periodization cannot be used. You need this temper distribution delta t hat. Okay. Now let's generalize this tiling by the integers business to higher dimension, where it becomes more interesting. So we start with a lattice. So let capital T be a lattice. What's a lattice? In our case, it's a linear image of the integers, where A is an invertible matrix. In other words, it's a discrete subgroup of Rd, which linearly spans all of Rd. You want to have D linearly independent vectors with it. And together with the lattice T, we usually look at the so-called dual lattice, which is take the same matrix, invert it, and transpose it, and multiply by Zd. So here are two pictures. This is T, and this is T star, the dual lattice. If you take this lattice and you expand it, make it thinner, this will become denser, right? If you spread out one, because of this inverse here, the other guy becomes denser, and vice versa. Okay. Now, for the lattices in general, we have the so-called Poisson summation formula, which I'm sure you have seen before in this form. You usually see this Poisson summation formula in this form. If you have a function f on the real line, and you add it on the integers, you get the same as if you're adding f hat on the integers. This is the Poisson summation formula in one dimension, but in many dimensions, this must be converted to a sum over a lattice, and this will be a sum over the dual lattice with a constant here. What's the right constant? It's exactly here. So view this as tempered distributions, and it says exactly this. But if you take, now imagine you have a Dirac mass at every red point, and you take the Fourier transform of this distribution. Well, you'll get this. You will get this. But you're going to have a number on each one of them. Which number? 1 over the volume of A. So the larger this is, the taller the Diracs here will be. The lower the Diracs here will be. This is Poisson summation. Which, in terms of tiling, means what for us? But if you're trying to tile with a tile F and the lattice, so you want this convolution to be a constant, then you want F hat to vanish on the Fourier transform of delta t, which is essentially delta t star. So you want your function to vanish, your Fourier transform to vanish on t star, except at the origin. The origin is always fixed. So you want to tile with this. For instance, if you take a shape like this, this will tile with the red dots. If you take the Fourier transform of this shape, it's going to vanish at all the blue points here. Okay, and now we come to the first theorem, which FUGLEDE himself proved. Not in this language, in the language of periodization, but I want to show it in our way. So, FUGLEDE himself proved his own conjecture in the lattice case, meaning what? He proved that whenever you have a set omega, then it tiles with a lattice T if and only if the frequencies corresponding to the lattice T star form a spectrum. This goes both. So it's like the general FUGLEDE conjecture with the word lattice thrown on both sides. It becomes correct. And we'll see the proof now. So here the set omega, which I have shown, tiles with lattice T. So how I constructed it, I took the square and I cut off a corner and I moved it over by 1. It's very easy to see that if you translate by all integer coordinates the screen shape, you will get exactly everything covered exactly once. So this is the omega for which we're going to prove it has a spectrum. Which spectrum? The dual of this lattice. And how do we prove it? Okay, first of all, we're going to assume that omega has volume 1. It just makes it unnecessary to remember whether you have to multiply or divide by something. And we have to look at this object. I don't know, maybe this display prevents some people from seeing. Okay, so we have to look at this object because the FUGLEDE, in order to have a spectrum, this guy must be able to tile. So what is this guy? It's the Fourier transform of 1 omega convoluted with 1 minus omega. Now this function here is strictly non-zero, exactly in omega minus omega, the interior of it. Therefore, the vanishing set is outside this. So if you call this function f, little f, then this is f hat. And where does f hat vanish? Outside omega minus omega. Okay? So let's see how the proof goes. So let's start from the spectrum side. And we go with equivalences to the tiling side. So let's assume we have T star as a spectrum. Meaning what? According to our interpretation of the spectrality as a tiling condition, it means that the power spectrum of omega tiles with T star at whatever level it has to tile. So this is our starting point. And now, since we have a tiling here, how can we test this tiling? Well, the object is this, so we look at its Fourier transform and at its zero set, which is, as I said before, the zero set of the Fourier transform of this guy is the complement of omega minus omega. And therefore, delta T star hat must live there. But delta T star hat, by Poisson summation formula, is the support. It's exactly this, delta T. So T, which is the support of this, must be contained in the complement of omega minus omega. Now let's rewrite this as T minus T intersect omega minus omega is just the 0 point. Why can we do this? First of all, because T is a lattice, so it's a group, so T minus T is T. T is a group, so T minus T is the same as T. So what this says is that if I take T minus T and I do not accept 0, then if I intersect it with omega minus omega, I will only see 0. Exactly this. And this is what we call a packing condition. This is equivalent to packing. Perhaps it's worth doing this in a little detail. I'm sure all of you have seen it before, and many of you have forgotten about it. So we have omega translated at the locations T. When do these form a packing? When you have nothing represented twice. So you cannot find a situation like this unless omega 1 is omega 2 and T1 is T2. Now collect the T's from here and the omegas from there, and this becomes that you cannot find a solution to this unless both sides are 0, which means that omega minus omega intersect T minus T can only contain 0. This is exactly equivalent to packing. So what we proved there is that omega plus T is a packing. There are no overlaps. So we have a domain omega, which is of volume 1, and the lattice, which is a periodic set, of density 1, which gives you a packing. This can only happen if it's a tiling. Why? So you have your object and you repeat it periodically. And this has volume 1. And these locations have density 1. And nothing is covered twice. which means if you take a huge disk, the level you will see is at most 1. So the volume you will see in this huge disk is, well, huge square, say, is r to the d. I have destroyed all the available chalk for some reason. So take a huge square of side r. You have volume r to the d. This function in there is bounded by 1. And at the same time, you have about r to the d points of t, because it has density 1. Each of them of mass, of integral, whatever you want, 1. How can this be if you have a gap here? If you have a gap here, it gets repeated periodically. It's going to eat out of your total fraction of your total volume. So there's nothing, no gap there. No gap means tiling. You cannot omit something periodically and still have identity of volume times density equal to that. So it's a tiling. Oops, sorry. It's a tiling. And we have proved our equivalence. T star is the spectrum if and only if omega plus t is a tiling. This is the lattice FUGLEDE conjecture. Okay. Now, this is one of my favorite examples. So we're leaving the FUGLEDE conjecture again. I'm just going to give you another demonstration. This is a little more work than the Scottish book problem, but it's, I think, a little more impressive too. How we apply the Fourier transform to solve the tiling. So here's the problem. I have a big box, a big rectangular box, dimensions q1 times q2 times q3. And I want to fill it with bricks. And I have large supplies of two kinds of bricks, brick A and brick B, of fixed dimensions. A1, A2, A3, B1, B2, and B3. Or I could even, in the proof later on, I'll just do the proof in 2 dimensions because it's just easier. So I want to fill this box with these two kinds of bricks. When is this possible? Here's the theorem. This is only possible if you can, so this is your big box. If you can cut this way or that, and fill this with type A and this with type B. You cannot have a properly mixed brick filling of your box unless there's also a simple brick filling. This is the theorem. So for instance, suppose this is the big box, and we have a filling with type A and type B, like this one. Sure, this is possible, but if this is possible, then something like this is also possible. So you cut the box in 2 pieces, use brick A for one, brick B for the other. That's always possible. This is our theorem. Now, Bauer and Michael did not prove it, as I'm going to show. They proved it using combinatorics. But I'll show you the Fourier analytic proof. Okay, again, this is our Fourier transform. Now, my proof will work in 2 dimensions. So the theorem is just fine in 2 dimensions. The proof is the same in d dimensions, but the figures are easy. So this is the Fourier transform in 2 variables. Now, if I have a box, this is my large box, or any box, which is C1 times C2, then the Fourier transform, you can do it very easily. You can compute it. It's a tensor product of the function of C and the function of eta. This is the function of C, and this is the function of E. And what are the zeros? It's very easy to find them because it's a product. The zeros look like this. So this length is 1 over C1. This length is 1 over C2. The dotted lines are not part of the zeros, but the solid lines are part of the zeros. And why is this? Because this function vanishes on every multiple of 1 over C1 except at 0, because at 0 they cancel out. It's 1. Okay? So the zero set is as you see it there. The solid lines are part of the zero set, but not the dotted lines. Okay? And this is true for any box, both for the large box and for the small box. So the zero set, if xi eta is part of the zero set, if and only if either xi is a multiple of 1 over c1 or eta is a multiple of 1 over c2. It's very easy to comprehend. So let's now express our filling condition. So you have brick A at locations T, brick B at locations S, let's call them. So this is filling. You want the indicator function of the big box to be the sum of the indicator function of the small boxes. Okay? That encompasses everything, both the disjointness and the covering. Now, I'm going to encode the sets T and S, as I usually do, by Dirac masses. We put one Dirac mass on each. And then this condition can be rewritten as a convolution. So the function 1q is a convolution of delta t with 1a and delta s with 1b. And whenever you see a convolution, what do? Take Fourier transform. So if you take Fourier transform, you will get a Fourier transform of the big box on the left and a sum. Now this is the Fourier transform of each of the small bricks. The phi t and the phi s are the Fourier transform of delta t and delta s. What are these? These are trigonometric polynomials. Each of them is a finite sum of Dirac masses. If we go to the Fourier side, we'll get it to a finite sum of exponentials. So trigonometric polynomial. These will play absolutely no role in the proof. That's why I don't say more. But what we can see from here is that if you have a common zero of this function and this function, it will also be a zero of this. Correct? No matter what the phi do. So common zeros of 1a hat and 1b hat will also be zeros of 1q hat. And the zeros, let's now take the box q to be a unit, a centered unit square, this one. And then the zero set, from what we said before, is exactly those points of the plane where one or the other or both frequent or the coordinates are integers, non-zero integers. Okay, so xi or eta must be a non-zero integer for this to happen. These are the zeros of 1q hat. Okay. Now let's suppose that we take this point, 1 over a1 and 1 over b2. Now, this point, I claim, vanishes on both 1a hat, it's in the zero of this and of that. Why? Well, it's in the zero of 1a hat because the first coordinate is a multiple of 1 over a1. And it's in the zero of 1b hat because the second coordinate is a multiple of 1 over b2. So that point up there is a common zero, therefore it's a zero of 1q of the big box. And the same is true for 1 over b1, 1 over a2. Okay? So this point is in 1q hat zeros, and this point is in the same set. By what we know about the zeros of 1q hat, this, we know that this is true because of that, and this is true because of this. Okay? An end of two ors. In how many ways can this happen? Let's see, the easy case. What happens if this is true from the first bracket, and this is true, and this is true from the second bracket? 1 over a1 and 1 over a2 are integers. Well, we're very happy because in that case we can fill the big box with just copies of A. If you have this being a 1 by 1 box and you have a little brick here where this is, say, 1 over 5 and this is 1 over, I don't know, 9, how do you fill it? Well, you put 9 times this way and 5 times that way. So in this case, we can use just brick A. And in the other case, meaning this ballot and this ballot, we can use just brick B. And we're done in this case. But other cases are also possible. Let's take this one, which is indicative of the other one too. Suppose this is true And this is true. 1 over A1 and 1 over B1 are both integers. Then I claim this is true for some integers K and L. How do I do this? Okay, 1 over A1, 1 over B1 are integers. Just draw any line going from bottom to top. You will be encountering, as you're going from bottom to top, either brick A or brick B. So you will be adding either a length A2 or length B2. And in total you get 1. Therefore, K is the number of A bricks you saw on the way, L is the number of B bricks you saw on the way, and that's equal to 1. Okay. This is true, therefore, for some K and L. Alright, now cut at this length, where this length here is KA2, and fill this, okay. Your brick A1, A2 has no problem filling upwards because 1 over A2, has no problem filling this way because 1 over A1 is an integer. So you repeat your brick 1 over A1 times. This is no problem. How about this? Well, this is definitely no problem. It's an integer times A2. So you have K levels of brick A and L levels of brick B. And the other case, you just have to cut the other. Just by looking at the zeros, you get this theorem. And this works in dimension D, if you are a little more careful. No big difference. Okay? Now let me also point out that this theorem is not true for 3 bricks. If you can have a tiling of the big box, a filling of the big box with 3 types of bricks without this being possible to cut the box into 2 parts and fill one part with a subset of the bricks and another with again, a subset of the bricks. And it's easy to see why this works for these 3 bricks. So these are the 3 types of bricks. This is the one covering. It's easy to see that no matter if you cut this way or that way, and no matter which proper subset of these you choose, you will never make it. Okay, because the lengths are so good that you can never. I'll leave this to you to check. All right. Now, before going into this, I think I'll stop and do this over the next hour.
Any questions or comments? Okay, I have one. About this theorem about with the boxes.
Yeah.
Is it for other type of, say, for other shapes? Do I know something?
For other shapes. People do not make boxes of other shapes. They're always rectangular.
No, I mean...
Not to mention bricks.
The triangles, for instance.
Yeah, okay. I haven't really thought about it. I think for triangles, you have to struggle to make a meaning out of this.
Yes, because you can always... Yes. Maybe triangles is not a good example.
You're right that some meaning could be given, but it might be that it's so restricted that such a theorem, if true, would not be unexpected. As this one is. But I really don't know. I haven't thought about the shapes.
Okay. Okay, thank you.
And the last one, is parity important or something? I mean, if you
no,
try
because
4
you need
bricks.
dimensions. Oh, 4 bricks?
Yeah. I mean, is parity doing something?
I don't think so. I think with 4 bricks,
Will not be also true.
there will be also another. I mean, if I go to the shape, if you want to make an example, 4 bricks, and I could go here and I replace this long brick with 2 bricks, say this cut at a random point, then this would remain valid, but instead of 2 bricks, you would have, if 1 brick, then we have 2, so in total you would have used 4, but you would still not be able to tile anything smaller in the subset. I mean, if you cut to a random point, there's no way you can use it in any other way than this.
Yeah. Thank you.
And you haven't used so that you have this A because you represented timings as a linear mapping, a linear matrix applied to the picture.
You're not talking about this problem, right?
No, in the beginning you said that any lattice that you consider is A times integer lattice. So you haven't. Did you use this property somewhere?
We use this when we prove the lattice FUGLEDE conjecture. So FUGLEDE conjecture is true if you assume tiling with a lattice. It implies it is equivalent to having a lattice as a spectrum. There A is used, but I didn't actually write it down because I only used the language of T and T star. So it will. Yes, it does.
Okay, then any other question? Then we can continue in 15 minutes. Right? Okay. Thank you again.
Huh?